Hello, everyone. So in this tutorial, we'll be talking about Lab 2. So in Lab 2, basically, there are two tasks, two main tasks. In task 1, we will be simulating an incrementer circuit. And in task 2, we will be simulating a simple 3-bit ripple carry adder. Okay, and and these tasks are divided into two parts. So in task 1, we will simulate or design the incrementer circuit using built-in components like built-in adder. And we will also do the same thing using our user-defined circuit block. Okay, so we'll talk about them in details in a moment. So user-defined version of the incremental circuit and built-in version of the incremental circuit. And similarly for task 2, we will have them two parts. In the first part, we will be using the built-in version, I mean built-in components. And in the last part, we will use user-defined sub-circuit to implement 3-bit ripple carry adder. So let's jump into that. And now let's briefly explain what an incrementer does. I mean, what is the function of an incrementer? So this we will be designing a 3-bit incrementer. So suppose you have a random binary number. Let me represent them as x2, x1, and x0. Suppose this x2 is the most significant bit and x0 is the least significant bit. So suppose let's take random values like 0, 1, 1. Suppose this is a random input, and incrementer will do what? It will just add binary 1 with the input. So suppose the input is a 3-bit binary number, and it will just add 1 with this 3-bit input. So that's basically an incrementer, a very simple function. So to add 1, you basically need adder, right? As you can see, the task 1 part A is using built-in adders. So we will be using built-in adders to make incremental circuit. Let's do that. So we have to take adder. So where can we get the adder? Here in arithmetic section, right? So let's take adder and place it right here. Okay, let me just zoom a little bit. And as you know that by default, this adder is 8 bits, so you have to make it 1. Okay, so this is an 1-bit. This is a 1-bit full adder. So as I have already mentioned, that we will be using a 3-bit incrementer. I mean, the input will be 3-bit and it will be incremented by 1. So that's why we'll need 3 of these full adders. So let's take another adder from here and place it right there. And let's take another one, place it right here. Okay, so as you can see in a full adder, so let's make them 1-bit as well. So okay, so there are 3 adders, full adders. As you can see that these are, if you hover the mouse on top of the pins, the pin name will be shown. So this is the output and these are the input, these are the input. Now let me show, at first let me show you that how does a ripple carry adder look like. So you have to design the incrementer using a ripple carry adder. So let me go back to the drawing board and let's draw the diagram for a ripple carry adder. This is like, okay, so we have C in, I mean carry in, and we do have 2 other inputs like A and B. Let me put A right here and B right here. These are the inputs for, let me write C in here. Okay. Okay, so these are the 3 inputs for a full adder, and you will have 2 outputs, 2 output pins. One is A, and the second one is like C out. Okay, and this is another full adder. Here you have C in, you have A, and you have B, and you have 2 output pins, A and C naught. Again, here sorry, this is C in, and this is A, this is B. Okay, and we have S or sum. These are the 3 full adders. So to make a ripple carry adder, we need to just connect this C naught, I mean the output of this full adder, to the input carry of this adder. I mean C naught goes to the C in of the next adder, and C naught goes to the C in of the next adder. So if you have more, then you have to connect like this. I mean, C naught goes to the C in of the next full adder. Okay, so so here, like these, so these are the three sums. So let's name it as S0, let's name it S1, and let's name it S2. Okay, so and we will place the inputs right here. So we told you that there will be a 3-bit input. So suppose this is the 3-bit inputs are like x3, x2, no, sorry, x2, x1, and x naught. So these are the bit positions. So this is the most significant bit, this is the least significant bit, and this is the middle one. So suppose we have inserted x naught input to this adder's input, and then let's put x1 right here, x2 right here. So this is the 3-bit input. So our task is to increment this binary number by 1. Okay, to do that, so this is actually an error, as I have mentioned that this is a ripple carry error. So to increment this by 1, what we have to add? We have to simply add 0, 0, 1, because this is 1, right? So we have just added zeros to make it 3-bit, but this is just 1. So if we add this 0, 0, 1 to this 3-bit, then it will act as an incrementer. Okay, so it will just increment the 3-bit input x2, x1, and x0. So as you can see that these adders have one more input pin, like B here. As you can see, I have not connected B. I mean the second input of this adders. So this second input will take this 0, 0, 1. Okay, so we have to insert 0 here. We have to insert fixed 0 here. We have to insert 1 here. So this is the other 3-bit input for this 3-bit adder or ripple carry adder. Okay, so this is the first 3-bit number, and this is the second 3-bit number. So the function of this ripple carry adder is to add these two 3-bit numbers and generate the result. So the result will be generated right here. Let me use another color. Yeah. So these sum S0, S1, and S2, and the last carry, I mean the C out of this last adder, will generate the output. I mean this one, including this one. So the output will be a 4-bit number, right? Because if you add two 3-bit numbers, there will be a carry out. So that's why. Let me show you with an example. Maybe suppose you have 1, 1, 1. I mean this x2 is 1. Suppose x1 is 1, x naught is 1, and you have 0, 0, 1, and then you have 1. 1 plus 1 is 0. 1 plus 1 is 0, and 1 plus 1 is 0. So the result would be a 4-bit number, right here. Okay. So this carry out will be this number. Okay. So we can also treat this C naught or C out as S3, so that we can represent the result like this. I mean S3, S2, S1, and S0. Okay. Okay. So in this way we will design the incrementer. Let's just implement this thing in Logisim. Okay. So we have 3 full adders, and let's take the inputs first. So there are 3 inputs: input number 1, input number 2, and input number 3. Okay, and let's connect the inputs first. Okay, so this is one of the inputs. Let me zoom it a little bit. Okay, so this is one input of the adder. Let's connect the second input to this pin, and let's connect the third input pin. Okay, so these are x2, x1, and x0. Let's label them. So the first one is x2, then x1, x0. Okay. Now let's connect the carry pins. So in the ripple carry adder configuration, the C out of this adder will go to the C in of this adder, and the C out of this adder will go to the C out of this next adder. So let's connect it like that. C out is coming from here and goes as the C in like here. Let me clear this extra thing. And then again, C out of this adder will go to the C in of this adder. So this way the carries will be connected. And you should remember that for an incremental circuit. So this will be the input, I mean x2, x1, x0. and there will be the second 3-bit number will be 001 because we have this 001. This is constant for an incremental circuit. So we will use a constant symbol or pin here. So you will find this constant symbol if you expand this wiring section. So let's take constant pins here, just select and place it somewhere on the canvas. And now let's connect this pin to the second input. Let's take like this. So, okay, so we have to add 001. So this should be 0. Okay, so currently it's 1. So to change this thing, you have to select it and then go to here. After this cross sign, you have to write 0 to make this a constant 0. I mean, constant 0 input to this adder. And then let's take another constant and connect it here. Okay, and it should be 0 as well. So let me make it 0. Okay, then let's take another constant here. This should be 1. Okay, because we are adding 001. And now, what pin we have left? Okay, so these are the sum pins, right? Okay, so these should let's take output pins here. Let's connect this. So this is the sum pin of this error. Okay, let's take another output pin here. Let's take another output pin right here. Okay, and as you should remember that this one is S1. So let's level them maybe. So let's select this thing and let's level it as S0. Okay, and let's level this as S1, and this is S2. Okay, and we have S3. Okay, so let me remind you that the carry out pin of this last error will be treated as S3. I mean, the summation result, the carry out summation result. Okay, let's put a uh, output, sorry, output pin here. So, okay, so let's level it as S3. Okay, so S3, S2, S1, S0. This is the output value of this incremental circuit. Now, so we have one more connection left, the C-in of this first error. So the C-in should be like 0 because initially there is no carry in. So let's put a constant here. Let's connect this and make it 0. Okay, so this is the carry in 0. So we hope that the circuit is complete. Now let's test the functionality of the circuit. So what should be the functionality of this circuit? So as let me put the drawing board and the Logisim side by side. Okay. Yeah. Okay. So what is the function of this incrementer? So whatever the input is, I mean x2, x1, x0 is the input. So let's show the results with the truth table maybe. X2, x1, x0 is a 3-bit binary number which is working as an input, and we are adding 1. Okay, because as you can see, the second input set, I mean second 3-bit input is 001. So the incrementer should add 1 with x2, x1, and x0. So let's put 1. And what should be the output? We will analyze that. Okay. So what is the first combination of this 3-bit input? It's 0, 0, 0. So if you add 0, 0, 0 with 1, the output should be, I mean, the output is 4-bit, S3, S2, S1, and S0. So the output should be like this. Because if you add 0, 0, 0 with 1, you will get this is 1. So 0, 1, 1, 0, 0. And if there is no carryout, the carryout should be 0. So this should be the output. Okay. So the output is 0001. Let's check this. So S3. So let me write S3, S2, S1, and S0. So here, S3 is 0, S2 is 0, S1 is 0, and this is S0, S0 is 1. So this is the functionality of the circuit is matching with the theoretical results. So let's roll. I mean, let's move to 001. Next combination is 001. If you add uh, 001, and if you add 1 with this, I mean, if you increment this 001, what will be the result? So 1 plus 1 is 0, and then 1, then 0, and you don't have any carry out, so that will be 0. So the output should be 0010. Let's take that. S30, S20, S10. Oh, okay. I have not changed the input here. So let's change the input. So input is 00 and X naught should be 1. Okay. So let's toggle this. So you have to use the poke function here. So, okay, just select there and then change the value. And so 001, the result should be 0010. As you can see, 001 and 0. That is matching. So in this way, you have to check all the combinations. Like this, the third combination is 010, then 011. In every case, you have to add 1 and check the output result. Okay, the circuit should generate the expected output. Okay, so this is an incremental circuit. So so far we have used these adder blocks, which which was already built in, was already available in these Logisim library. But we in the task 2, I mean, this is task 1 actually. In the task 2, you have to use your own subcircuits. So these are called subcircuits. I mean, inside these blocks there are some circuits. So that's why it can be called subcircuits. But the subcircuits, I mean, we did not design the subcircuits inside this adder block, right? But if we want to create a subcircuit and use that subcircuit as a circuit block, we can do that. So this is actually the part 2. I mean, where we will design our full adder circuit and then we will use we use that circuit or subcircuit as a circuit block to make bigger circuits. Okay. So to do that, let's go to the project and before that, let me open a new project because and save this thing. I mean, this part 1. Let's save this part 1. Okay, now let's open a new project and we will be using our own circuit, okay, circuit block. So to make your subcircuit, I mean user-defined subcircuit, we're calling it as user-defined subcircuit. So let's go to the project and now add circuit. You have to put a name like I mean it like this. My full adder. Okay, and then your named. I mean I have just named the subcircuit here that should appear right here. Okay, the subcircuit we just have named that should appear right here. Okay, under main. I mean after main. So you have to go to this my FA in this subcircuit. Now you have to draw. I mean, when you are creating your subcircuit, you must select this. I mean, your subcircuit name. Okay, so then I can design my circuit. Okay, so here, what will I design? I mean, I will design a full adder. Okay, what is a full adder? I mean, previously we have used the built-in full adder, but in lab 1, you have seen that we can design a full adder using logic gates like XOR gates, NOT, and or something like that. So using logic gates, you can design a full adder. You have done that in lab 1. So I am not repeating that just to make this circuit right here. So what I have done here actually, so I have just copied the circuit from the lab 1 and just pasted it right here. Okay, so you can just select like this, and from keyboard you can just press Control plus C and Control plus V right here. The circuit will be pasted. So this is a full adder that we have designed. I mean, we designed in lab 1. So we are reusing that circuit. So as you can see, these are the two inputs. A, B are the two inputs, and there is a carry input as well. And the output is a sum bit and the carry out bit. So this is under the subcircuit my FA. Okay. So and now you do not have to save anything. Just go back to the main. Okay. Go back to the main circuit. So I will just this is important. Just go to the main. You can double click on the main, and then you will come back to the main circuit page. So that my FA was a sub-circuit, and you will be using that my FA in your main circuit. This is our main circuit page. Okay, so how to call that I call that full adder circuit. I mean our design full adder circuit, which was in my FA. So just like a component, you have to select my FA, and then if you take the mouse on the canvas, you will see that there is a rectangular block. This block is your design circuit in my FA. Okay, So if you put here, you will see that there are three inputs. Let me zoom in a little bit. Now, if you hover your mouse, you can see maybe here. You can see you have to just place your mouse, and you can see this is A, this is B, this is C in, and this is S or sum, this is C not or carry out. So this is our design full ladder, and we have to take three of them, and the process is exactly similar. Okay, now we have to insert the input. I mean the first 3-bit input. Let's put them. So this is an input pin. Let's connect it right here. So this is my A. If you place the mouse on the pin, it will show this is a pin A. Okay, and let's put X1. So this was X2. Let me label that instantly. X2, and this is X1, and we have to take another one. Okay, let's label it as X0. So this is the first 3-bit input. Okay, now we have to connect the carry pins. So I think this is the carry pin. As you can see, this is C0 is the carry out pin. So what was the connection? Like you have to connect the carry out of this adder to the carry in of this adder. Okay, so which one is the carry in pin? Let me put the, yeah, here you can see that if I place the mouse right here in the third input pin, this shows as C in. So I have to connect the C out of this full adder to the C in of this adder. So this is the design of Ripple carry adder actually. So now let's connect this C out of this second full adder to the carry in pin of this first. I mean this the next full adder. So C out of this thing will go to the C in of this thing, and C out of this thing will go to the C in of this thing. Now, as this is an incremental circuit, as I have mentioned, so in this 3-bit adder, you have to add a constant 001 as the second 3-bit input. So let's take constant pin from here and connect it to the second input. Okay, and we have to make it 0. The process is exactly same as part 1. Okay, okay, let's take again a constant which should be connected as the second input. Okay, this should be 0. And another constant which is 1. Okay, so we have added 001. I mean, we have set this to add 001 with this 3-bit input, which is x2, x1, and x0. And now here, one pin, one C in of this first adder should be connected to 0 because we don't have any carry in initially. So we have to put constant 0. Let's make it 0 first. 0, and then connect it. Oh, these are connected, so we do not want this to connect. So let's take a different route. Okay, so we have put a carry in 0 to this adder. Now, do we have any connection left? Yeah. So we have to put some output pins to see the results. So let's start from here. So this is the sum result for the first adder, and then this is the sum result of the second adder. This is the sum result of the third adder. And as I have mentioned that the C out of this last adder, we will name this as S3. Okay, so let's label them. Let's take this first and label that as S3. Okay, and label that as S2, and let's label that as S1. S1 is S0. Okay, so S3, S2. Oh, I think let's put it here. Yeah, S3, S2, S1, and S0. Okay, so let's check the truth table result maybe. So we have already. Oh, we do have a truth table. I mean, it should match exactly as before with the built-in version. Okay. Okay, so let's take the first combination where x2, x1, x0 is 0, 0, 0. So right now x2, x1, x0 is 0, 0, 0. Okay, and then if you add 1, then the output should be 0, 0, 0, 1. I mean, S3 should be 0, S2 should be 0, S1 should be 0, S0 should be 1. So 0, 0, 0, 1. Okay, let's take the second combination where x2, x1, x0 is equal to 0, 0, 1. Okay, so right now it's 0, 0, and we should make it 1 to change this or flip this to use this option. Now let's click on that. So now 0, 0, 1. The input is 0, 0, 1. So if you add 1 with this 0, 0, 1, the output should be 0, 0, 1, 0. So let's take that 0, 0, 1, and 0. Okay. So in this way, you have to check all the combinations, all 8 combinations of x2, x1, and x0, and the output should be the incremented value of the input. Okay. Now let's move to part 2. Not part 2, it's task 2. So we have to make a ripple carry adder. Okay. This is exactly, exactly same here. For the 3-bit ripple carry adder, let me go back here in the circuit. So we had 3 full adders, right? So in a 3-bit adder, suppose these are A and this is B. Okay, this is A, this is B. These are input. Input pins. Okay, this is B. So for the first case, in task 1, this was one input, 3-bit input, and in task 1 you had incrementer. So for incrementer, the second inputs are like this, right? 0, 0, 1. But for making this an adder, it's simple, right? Because you have, in that case, if you want to make an adder, the circuit will be exactly the same, just the input will be different. Here you will have y2, y1, and y0. Not fixed 0, 0, 1. Instead of fixed 0, 0, 1, you will have variable input values, right? Exactly same as x2, x1, and x0. Okay, suppose you have something like this 0, 0, 1, and the second input is like 0, 1, 1. So you have to add this. Okay, so this circuit, the circuit we designed for an incrementer will work. Will work perfectly for this addition operation. Okay. Okay. So for an example, let's take this combination. Okay. So what should be the result of this addition? 0, 0, 1, and 0, 1, 1. Okay, so what should be the result? So 1 plus 1 is 10. So we have 0, we have a carry out 1, 1 plus 1, 10, 0, 1. So 1, 0. And there is no carry out. So we have to put 0 as the fourth bit. So this should be the result. Okay, if we insert 0, 0, 1 here as x2, x1, and x0, and 0, 1, 1 as the second 3-bit input, the result should be like this. Let's check this with our adder. Okay, so let me put them side by side. Okay, so let's put 0, 0, 1 in this adder. I'm using this exact same circuit as incrementer. I'm using this incrementer circuit. Okay, so to change the incrementer circuit to a 3-bit ripple carry adder, you just need to. This should not be a constant now, right? Because for the incrementer circuit, these are constant like 0, 0, 1. But right now, if we want to add 2 3-bit numbers, we have to make them variable as well. So to make them variable, so to edit the circuit, you have to go to this selection mode here. So I'm selecting this arrow, and now you can change the circuit. Edit the circuit. Let's delete them. Let's delete the constant inputs. Okay. And instead of the constant input, let's take some output pins. Input pins. Okay. So this will be exactly. This will be inputs like this x2, x1, and x0. Okay. Yeah. Let me take the second input, third bit. Okay. Now let's go to the poke mode. Now, what is the combination? 0, 0, 1. So x2 should be 0, x1 should be 0, and x0 should be 1. So 0, 0. Let's change that to 1. And then what should be the second 3-bit input? 0, 1, 1. So currently this is 0, and this should be 1. This should be 1 as well. Now, here, the output should be like this should be the S3, this should be the S2, this should be S1, and this should be S0, right? Okay, so S3 is 0, S2 is 1, S1 is 0, and S0 is 0. This is matching the theoretical addition result, right? 0, 1, 0, 0. So 0, 1 0 0. So this is working perfectly as it should. So that's how you will make a 3-bit triple carry error. So you have to do this same thing. This is the built-in version. I mean, I have used built-in adders to make this circuit. Um, this is working, and you have to also do that for user-defined circuit. Okay, I mean user-defined version. The user-defined version should work exactly in the same way. Okay. So this is all from me for Lab 2. Thank you for your attention.